Have you ever wondered about the difference between mass and weight? These terms are often used interchangeably, but in the realm of physics, they represent distinct concepts. Understanding the difference is crucial for comprehending the fundamental laws governing the universe. Mass, simply put, is the amount of matter an object contains. It's a fundamental property that remains constant regardless of location. Weight, on the other hand, is the force exerted on an object due to gravity. It varies depending on the gravitational pull. Imagine a cosmic dance, where mass is the dancer and gravity is the stage. The dancer's inherent qualities remain the same, but their movements and the forces they experience change depending on the stage's gravitational pull. This essay aims to untangle the intricate relationship between mass and weight, providing you with a clear understanding of these fundamental concepts and their significance in our daily lives and the vast cosmos.
Mass is the measure of how much stuff an object is made of. Think of it as the amount of matter packed into an object, regardless of its location in the universe. Whether you're on Earth, on the Moon, or floating in the vacuum of space, your mass remains constant. We measure mass in kilograms. A 1 kilogram object on Earth will still have a mass of 1 kilogram on the Moon, even though its weight would be significantly less due to the Moon's weaker gravity. To measure mass, we use a balance scale. This ingenious device compares the unknown mass of an object to a known mass, ensuring accuracy regardless of gravitational variations. Imagine holding a bowling ball and a tennis ball. The bowling ball feels heavier, right? That's because it has more mass. It contains more matter packed into its volume compared to the tennis ball.
Weight, unlike mass, is a fickle beast. It depends entirely on the gravitational pull acting upon an object. It's the force with which gravity tugs on an object's mass. We measure weight in newtons, a unit of force. On Earth, a 1 kilogram object has a weight of approximately 9.8 newtons. However, on the Moon, that same object would weigh only about 1.6 newtons due to the Moon's weaker gravitational pull. Imagine an astronaut jumping on the Moon. They would be able to leap much higher than on Earth, not because they have less mass, but because the Moon's gravity exerts a weaker force on their body. Weight is a direct consequence of the interplay between mass and gravity. The more massive an object, the stronger the gravitational force it experiences, and therefore the greater its weight.
Section 4. The interplay of mass, gravity, and weight. Mass, gravity, and weight are intricately connected. Mass is the fundamental property that determines an object's weight in a specific gravitational field. Gravity acts as the intermediary, dictating the strength of the attraction between objects with mass. Imagine Earth as a giant magnet and objects on its surface as metal filings. The more massive the object, the stronger the magnetic pull it experiences from Earth's gravity. This pull translates into the object's weight. The strength of gravity depends on two factors: the mass of the objects and the distance between them. The more massive the objects, the stronger the gravitational attraction between them. The closer they are, the stronger the pull. This explains why we experience different weights on Earth and the Moon. While our mass remains constant, the Moon's weaker gravity results in a significant reduction in our weight.
Section 5. Debunking common mass versus weight misconceptions. The distinction between mass and weight often leads to confusion. Let's debunk some common misconceptions. If I lose weight, I'm losing mass. When you lose weight, you're not necessarily losing mass. You're reducing the amount of force gravity exerts on your body, perhaps by losing body fat or muscle. Your mass, however, remains relatively constant. Weightlessness in space means zero gravity. Astronauts experience weightlessness in orbit not because there's no gravity, but because they're in a constant state of free fall. They're still being pulled by Earth's gravity, but they're falling around the Earth at the same rate as their spacecraft. Heavier objects fall faster than lighter objects. In a vacuum, all objects fall at the same rate, regardless of their mass. This is because the acceleration due to gravity is constant for all objects in a given gravitational field.
Section 6. Real-world examples, mass and weight in action. Let's solidify our understanding of mass and weight with some real-world examples. When you buy apples at the grocery store, the scale measures their mass, not their weight. This ensures you're getting the same amount of apples regardless of the store's location or altitude. When launching rockets into space, scientists and engineers must carefully calculate the spacecraft's mass and the amount of fuel required to overcome Earth's gravitational pull. In sports like weightlifting, athletes lift weights, which are essentially calibrated masses. The heavier the weight, the greater the force required to lift it, which helps build muscle and strength. These examples illustrate the crucial distinction between mass and weight in our daily lives and beyond. Understanding these concepts is essential for comprehending the world around us, from the mundane to the extraordinary.